Now it's my pleasure to welcome to the stage Ned Williamson.
All right, hello. Cool, it's working. Without further ado, let's just get into it. This talk is called Catch Me If You Can. Kind of cliche, someone else had the same phrase on one of their talks, so sorry. But we'll be talking about race condition fuzzing today. So just a quick intro on me. Been a researcher at Google Project Zero for a couple of years now. I like fuzzing as my research interest, and then low-level security, embedded systems, browser IPC, kernels as my, I guess, target of my research. So this talk, I'll be on theme with that. I'll be talking about research related to fuzzing, and then how we can apply it to kernel fuzzing on iOS. So the thing I want to start with is, this talk is mostly about addressing the problem of fuzzing for race conditions. And more generally, it's just about how to even deal with race conditions. And as someone who uses fuzzing a lot, I'm pretty biased. But just to introduce the problem, here's just a small snippet I took of some bugs that were reported by my team in the past couple of years. And then a couple of these, I think one of the Android binder bug and dirty cow I just put there. Just so you're familiar with, maybe there's some more famous bugs as well. But essentially, these bugs have been of high security criticality. And really, it's something we just continue to run into. It's something that we need to address, but we don't have any good tooling for it. So I know I was frustrated by this, and it's kind of over time I thought, how can I address this and bring some automation to discovering these issues without relying on luck or pure human ingenuity? So yeah, this is the problem. They're hard to find. So we don't really have any better way to find them than static analysis or auditing, which I would consider pretty similar and related. So a human auditor has to, today, realize that there's the potential for a race condition somewhere, or at least be aware of some specific pattern, and then maybe write a static analysis, maybe like a matcher on the syntax tree to find the specific case where a known buggy pattern occurs. But we don't really have a nice way to find race condition bugs in general. And maybe I shouldn't say in general, but we just don't have an automated way to do this for bugs that we can describe the problem when we see it, like we know when it crashes that there's a problem, but we don't have a way to actually search for those bugs without essentially knowing what we're looking for already. So that's the fundamental issue. And fuzzing actually is generally pretty good at addressing this category of problem. You don't necessarily need to know the form of the bug you're looking for. You just need to know the property that you're trying to violate. And so for security reasons, mostly we look at memory safety as that property. But earlier, teammate Ivan gave a talk on this XMPP stanza fuzzing. And there, he was trying to violate this property of consistency between parsers. So it's not just memory corruption. But generally, fuzzing is pretty good at saying, give me a property, give me a way to interact with this program, and I will try to find test cases that violate that property. And that's actually a very nice thing for race conditions or timing issues, because we might say, if we see a use after free, that's caused by a race condition, we don't need to understand how that happened. We know that fuzzing could observe it if it managed to trigger it. But then the question is, how do you actually fuzz? So to actually address this problem, we'll have to first cover how scheduling works. And don't worry, I'm just giving an overview because I didn't remember how any of this worked when I started this project. So this is kind of a quick overview. So I think that there's a kind of an important partition over types of scheduling that you can do to kind of consider what we can test well and what we can't test well. So what we can test well is cooperative scheduling, and this is where I'll start with this little demonstration. So how cooperative scheduling looks is that all the threads are cooperating with each other. They yield explicitly. So say in this case, we start execution in thread 1. this will continue along, and at some point, this thread says, I'm ready to yield. That goes to the scheduler, and at this point, the scheduler can decide, OK, I'm either going to switch back into thread 1 and continue, or go to thread 2. In this case, we'll go to thread 2 and execute all the way to the bottom. There's no yield statement, so then this thread terminates, and we go back to the scheduler. And then the scheduler says, OK, well, only thread 1 is runnable in this little example, and so we just go there and continue. So now if we look at how preemptive scheduling works, it's actually very similar. So we have the same example, continue along. There's some explicit yield. Maybe we're blocked on a lock. Maybe we just literally yield. This is a syscall on some platforms. Go to the scheduler, same thing happens. But in this case, at some point during the execution of thread 2, we get a timer interrupt, or some other condition happens that preempts this thread. And so this causes us to go back to the scheduler, and the scheduler is faced with the decision again. Out of these two runnable threads, which one do I run? And here it might decide to actually continue with thread 1 and then resume. This ends, and then we come over to thread 2. So the important bit is that if there are assumptions about, or if there's any safety issues or assumptions between the two threads that don't respect the fact that these preemptions could occur anywhere, then we may have a bug. And so we want to be able to address this problem with fuzzing. Now, the interesting bit, and I guess my philosophy is I always try to start with something that I know works well and slowly add to it to strengthen or broaden what I can do. So this is why I started with cooperative scheduling. You'll probably notice that these are essentially really similar. They both have an execution context, which is just a generic way of saying a thread. They both can block or yield to a scheduler. And the only difference really is preemption just, again, has this additional property where at any point you have these yields that just kind of appear caused by interrupts, or again, other conditions could lead to it. But this is a problem for fuzzing because this is hard to control, and it also can lead to exponential blowup. So the good news about cooperative scheduling is that it is easy. Cooperative scheduling, because it runs in order, if you think about that first example, there's no random yields popping up. It's all explicit. So as long as you're running the program, and if you have a deterministic scheduler, there's no randomness at all. You can run the same test case over and over. And it turns out that this is something I leveraged back in 2018 when I did a Chrome sandbox escape exploit. And I think at that point I was realizing, like, oh, there's something kind of interesting here, but maybe multi-threading will never be doable. But at least when you have different tasks that are running asynchronously, this kind of cooperative thing, there's really no issue for fuzzing needs. So again, when we get into preemptive scheduling, where most programs live, or a lot of programs live that we would like to fuzz, this is something that's super hard to model. Like, say you have multiple cores, threads running simultaneously, or even a single core and these random preemptions and switching. We really have no control here. And even if we did, we still have to search this exponential search space at every single instruction. And again, with the tools we have today, if we even hit a bug by luck, there's no guarantee it will reproduce. So we just have to cross our fingers and hope maybe we hit something. And this has happened to me. I have just stumbled into race condition bugs. But it always bothered me that they weren't predictable. So just to make it a little more clear, my initial work from 2018 and on to about 2020 was that I would deal with this problem by converting preemptive targets to cooperative targets by hand. And so what that means is whenever I was fuzzing something that, say, had a garbage collecting thread in the background, I just simply wouldn't spawn that thread. I would just run the main thread. And at the end, I would say, well, let's randomly run garbage collection, just call that function. But there would always be just one thread running. And so the nice thing is this is super easy to implement in like a hacky way for different fuzzing projects. I used this on Android NFC because their threading model was simple enough I could just replace with a cooperative scheduler. but the problem is on larger targets that are more complex, real world, well, Android's real world, but you know, the rest of the world, it gets really hard because we can't support blocking if you simply just don't spawn a thread and you don't do the work that thread would have done at this very coarse-grained high level. We just have no way to handle. Say you call some syscall that you're fuzzing and it blocks. Well, there's no notion of background work. Like now you are the background work and something else has to happen. So I had this idea that, well, why don't I at least try to create a deterministic threading library, so at least I can spawn multiple threads. They're really not going to be running actually in parallel. They'll all be on one CPU, but at least I can switch between them and kind of get around the blocking problem. So to implement this, I thought, well, OK, let's do what already works. We use only one thread. You know, we already have multi-threaded programs running on one CPU. This is a reasonable thing to assume for testing. And we're going to need to interrupt anything related to scheduling and multiple contexts. So in this case, this is basically anything related to threads or sync primitives like mutexes, reader-writer locks, condition variables. And then we just create our own scheduler that kind of owns all this context. So it will own the threads that exist, which ones are runnable. The mutexes and sync primitives will interact with the scheduler and let it know my thread's blocked waiting for this other thread to finish. And so if we have these components, we can at least encapsulate all the things related to multi-threading, and then we can just make this deterministic just for testing. So far, nothing new here. I guess the project I began working on I call concurrence, but it's still kind of TBD how to name this. I don't know, but it's sticking. So essentially what I did is I created these few components to help me with this problem. The first is an executor, which essentially provides the subprimitive of creating, deleting, and switching between threads or contexts. And then a scheduler that will look at these contexts that are runnable and say, you spawn a bunch of threads in the background, and then you own the scheduler object, and you just say, run a bunch of work for me until no threads are runnable. And then this way we can spawn a bunch of threads in the background for a fuzzing job, and then just run until they complete, then do some more operations, get some more work queued, and kind of keep looping. It's not highlighted well in the slide, but the second line under the scheduler bullet, randomizing the order of runnable tasks using fuzzer data, this is really one of the big insights here. So it's not just that we are, or I guess back in my Chrome days, when I was doing cooperative fuzzing, one of the things I would do is whenever the scheduler has a choice to pick some runnable task to run, I realized, oh, why don't we just kind of, if we're allowed by the model of that executor, why don't we just try randomly switching between them as opposed to just doing them in order? And so I included that idea here. So the scheduler not only just keeps track of what's runnable and switches between them, but rather than doing them purely in order, whenever we have a choice, we'll just pick a random task to make runnable, or not make runnable, but to switch to it. And again, this is kind of little details. We don't really need to go into annotation, semantics, and all this. But essentially, we need to support yield and block as fundamental ways to tell the scheduler which threads are runnable. And so this still hasn't really addressed this problem of preemption. And initially, I really had no hopes of dealing with this problem. I thought, well, if I can at least make some kind of deterministic scheduler, then my fuzzing will be reproducible. Maybe I can mess around with the scheduler here and there and find some stuff. But then I realized that preemption really is yields. And so I didn't initially realize this in the way that I showed it in the beginning. But if we already have to support blocking and yielding, a motivated researcher might be able to insert their own yields to a couple places. So even though preemption's off and everything is running until it blocks or running one at a time, if we yield in a couple interesting places, maybe we can let the fuzzer switch context around those areas and see if there's any race condition bugs. So that is, I guess that's posed a question of like, is this an idea that even makes sense? Can you turn off all random preemption and pick a couple places to do it and actually find a useful bug? And so I looked at a bug that I really was hoping I could find. I didn't try to find this bug, but I was thinking about this problem back in 2020, and I saw this bug report come into the Android bug bounty, I believe. And this was a user mode to kernel, I guess, RCE, privilege escalation vulnerability that I think was exploited. And this relied on a race condition. So I looked at the description of the patch. This is straight from the Linux changelog. And I don't know about you, but when I looked at this, I thought, oh yeah, no, definitely, this is too complex. Like, how can a fuzzer replicate this? You know. But then I saw the diff, and I realized this actually looks pretty simple. I guess what I was thinking is if I didn't know about a bug already being here in binder, what annotation, what yield statement might I been able to add? And so if you look at this diff, all that's happened is you had this function at the top where they took a lock, dequeued some work, and then unlocked and returned the work. And in the patch, they kind of show that the problem is this W type field that was part of the work became invalid. Like it seems like the W variable became freed after the lock was released. And so it seems like, oh, you only really need to preempt in one place to find this bug, or search around one preemption point. And that's right after the unlock of proc in the first function. So then I looked back at this description and realized that despite all the complexity where they're explaining how this bug came about, all that the fuzzer would need to do to find this issue is to preempt at those two places that I had hypothesized, where this inner lock, you can see the first bold statement. When we release it, on the next line, we acquire in thread 2. So we were doing something, and then in thread 1, we dequeued that work, and then we switched to thread 2. Thread 2 freed the node that we were looking at, and then released the lock, and then thread 1 didn't need to reacquire it, but it just continued running. And so I realized that the critical path is immediately after these two releases of the inner proc lock. So, you know, this is where I had a real insight that, like, you know, this is a bug that is critical. You know, we have no tools to find things like this, but it only takes one preemption, and it's a preemption in a place that seems obvious. You know, you have a whole subsystem that's really important that uses a lock in like 2 places. I don't think it's unreasonable to guess that a security researcher could say, well, given a fuzzer that can handle this situation, I'm going to guess, let's preempt before and after every lock. Let's preempt maybe in a few places. And then it really is quite a small search space to cover. And so this is the insight. We really need fewer preemptions than we think. And it took me a long time to understand what was going on here because so much of it was just like intuition and experimentation. But when I talked to people who know more about concurrency, I got this really great line from the author of a leak sanitizer, where he said something like, race-free programs have no observable behavior differences when preemption occurs between sync points. It's like, what is that? It just means that if the programmer got it right, if you only have preemptions around locking, that's enough to kind of see everything that can go wrong. And so, you know, don't worry too much about understanding this, but essentially, there is some kind of core intuition about like where locks are placed are around the areas where bugs are going to manifest, or it's very likely. So I thought, okay, that's probably good. And then if a researcher is skeptical of that, well, they can sprinkle a few yields themselves elsewhere, and no problem. So this is where I began to actually implement this by extending my existing iOS kernel fuzzer with this new project. So the initial sock fuzzer project, which is how I call this iOS kernel fuzzer, looks like this. Basically, I use libfuzzer as the fuzzing engine. You could really use anything, but what libfuzzer does is it collects coverage and mutates test cases for you, similar to AFL. And the type of input that it generates are protobuf messages that describe sequences of syscalls and other related things to one test case. And then it feeds these inputs to this fuzz target function. And then we call into the kernel in red with these syscalls in order. And then this project is actually a completely user space fuzzer. So if you've used something, if you're familiar with something like gvisor or a similar like user space based like containerization of a kernel, that's essentially what we're doing here. So rather than using a full hypervisor, we just kind of run everything in user space, and then so in gvisor, what happens is when your program tries to make a syscall, it goes into some Go code that handles the syscall for you, and you don't have to actually go to the kernel. So this is pretty similar, but for a hypervisor. So when the iOS kernel tries to access hardware, it just gets redirected to this hypercall interface that's handled all in user space. So the result of this is I just have this whole user space fuzzer. I wish I could talk more about it. I'm guessing like not everyone here knows about this, but unfortunately I just don't have time to go into details. So this is the existing project, and so to add deterministic threading support to allow me to do blocking syscalls, I added this concurrence code base. So what this does is I have this extra scheduler and executor. And so if I want to, or if the kernel wants to create threads internally, those are actually captured and sent to this hypercall interface. This is handled through the scheduler component that I talked about. And then ultimately, these kernel threads are just handled in user space by my, my new project, this deterministic scheduling. But the important bit is that the scheduler also has access to the fuzzer data. So on the right side, you'll see that arrow go up, get random numbers. So what that's demonstrating is that whenever the scheduler has an option between switching between a number of runnable threads, it will fetch a number right now. I mean, maybe in the future it'll be smarter, but now it just fetches like the nth. Give me the, it'll say like I have 10 runnable threads. Give me a number between 1 and 10. And it will draw that number from the test case. So the fuzzer can mutate that and then thus mutate the schedule. So now we're fuzzing along kind of two axes. You have the syscalls themselves and the data related to those syscalls and just the normal operation of a single thread in the kernel. But now you have this additional axis where the fuzzer can mutate the schedule of a given test case. And so just so you have a little more concrete idea of what this looks like, this is the data model for the fuzzer. This is just a protobuf message. So in the current instantiation or whatever, the current version of the fuzzer, I have 3 threads that each execute different syscalls. And then there's simply this bytes field that provides the scheduler data. So in each of these 3 threads, they get a pointer to these protobuf for the different commands that they handle from these different threads. We start running, and then the scheduler just says, OK, thread 1, 2, and 3 start out as runnable. Let's just run them. They'll execute some syscalls. At some point, they might block, yield, or maybe terminate. And so eventually, if we let the scheduler run until it's empty, we'll have run everything. And the interesting bit is that if any of these things cause some background thread to be created or to run, all that will all be interleaved and fuzzed along with the 3 sets of syscall threads. And then why 3? Originally it was 2, but I had 2 threads in one process, and then I decided to add an additional process with another thread to catch like cross-process race conditions. And this all sounds smart, but this is what it looks like. It's really just, I have my little scheduler thing. It's kind of a pretty simple project. And then to intercept the mutexes in X and U in the iOS kernel, we just have something that looks like this. So I just forward these calls to my virtual mutex, which is the one that works with my scheduler and handles the yield and block calls. But then I also have these additional yields before and after, like taking a lock and after releasing it, to kind of catch these type of issues that I was referring to earlier around locking. So we can kind of skip over this, but essentially, yeah, for each test case, I fork a process and then create threads in there, run, and then kill the process. And so if things go completely awry, it's all contained to a single process. So when I started running this, I quickly ran into a use after free bug. And it's interesting because it's in IPC, which is an area that's pretty interesting lately. And so I looked at, this is the test case that the fuzzer produced, and I had no influence over this. It's completely straight out of the fuzzer. So I don't know if I zoomed in or something. Yeah, so here's, I have a better format of it. But as you can see, it's fairly structured. But again, all I did was say, here are the syscalls. Here's what the structure of the data looks like for mock messages. Those contain this header with these enums in it. It has these fields that represent ports. And so I just kind of made a little description. And this was enough to run into this use after free. So if we look at an easier to read representation, what happened was we had, in the first thread, thread 0, we created 2 reply ports, which are kind of like file descriptors. Then mock message overwrite and mock message are the same thing. They just both send a message. And so this first message, it sends to the remote port, port 1, a message from port 2, and also receives. So if you see under options, it says send and receive. And we are making a send write for the port. So if you don't know about mock, which I don't think I even knew when I found this test case, all this means is like when we have these reply ports, we're allowed to receive messages on them, but we're not allowed to send messages from them because they're special ports that someone can reply to us with. So what this is doing is this is actually, in a roundabout way, the fuzzer realized, oh, if I create reply ports and I send this message to myself, I can give myself this additional write. So a human would never do this. They would just call, like, create a mock port, and it comes with both writes. But just to show that this was random, the fuzzer just stumbled into this pattern, and it was enough to find the bug. So the real bug comes in these next 2 messages. So in the first thread, we are sending a message to port 2 from port 2, and we're copying and moving our write to send messages on this port and the message. It's bizarre. And then from the other thread, we send, now that we have a write to send from port 1, we send a message from port 1 to port 2. I don't know if this even makes sense, but because we sent it here. But in any case, we create, let's see, so we do a move receive. So in this message, we're sending to port 2 from port 1, and we're moving our write to receive messages on port 2. I think, I don't know, it's confusing, but that's the point, right? So it found a way to erase these 2 last mock messages. And so I added a special print function to my project that indents based on which thread you're in. So I just put some prints around all over where the bug was happening. And as you can see, this actually turns into an interleaving table like you would see a human-written one. And so we can see that mock message was called from thread 0 and thread 1. And over here, somehow we end up copying in 2 writes. So I think that's where we send a message to a port from the same port. And then over here, where we did this move receive operation, it drops 2 references. So references go 3, 2, 2, 1. And over here, we end up dropping a reference and freeing, and then we end up freeing again. So, well, this is a real race condition bug. It's interesting. But what's really interesting is that it reminded me of a bug that my teammate Ian had found about a month earlier. And so when I looked at his report, he explained pretty clearly what the actual issue was. And he says that, basically when you send a message to a port from a port, X and U thinks, well, both of these are the same port, so we can do some operation the first time, and then if it fails, we return. If it succeeds, we continue. And it thinks, well, we already just succeeded on the same port. There's no way that it won't just succeed again. So they ignore the return value here. And it turns out that from another thread, you actually can do this weird move receive thing, I think, to break this assumption. And so you can race between these two calls. And this makes this fail, but then they don't realize it, and then things just kind of go haywire. And so this is Ian's handwritten message that he sent to Apple, and this is the way that they fixed it based on this report. And as you can see, it's pretty similar. I think he's got sending a message to itself, or from a port to the same port. And then we also have this receive write destruction with a move receive. And he has a different way of doing it. But it actually is the same bug. And it's interesting because I heard someone say that this bug was an example of a bug that you couldn't find with fuzzing. And I would have agreed with that if it hadn't just happened like that day that I heard someone say it. So not naming names, but the interesting bit, I guess, is if you keep running it, then on the new XNU code, it doesn't stop working. And so now over on the out of the mock message IPC world, let's go to BSD networking. Same setup, no special awareness, just this trick with yielding near unlocks. We end up seeing this other simple bug. So in thread 1, we call socket and set sockopt. In thread 2, we call disconnect X. And what's interesting is this actually is the same as the sock puppet bug I had reported a few years back. Same 3 syscalls. It just happens that before this there was a deterministic bug where if you set some option and disconnect, there's some use after free condition. Now there's a race between setting a different option called a flow divert token and disconnecting from another thread. And so here I transcribed it to C++. It's a little hard to read, but essentially I create a socket and then spawn a new thread where I just disconnect on that socket. And then from the first thread, send this packet. And then, there's a use after free condition. And the interesting thing is that I had no knowledge of this packet format. I didn't know what flow divert was. All I did was just call set sockopt with random data, and coverage guide fuzzing, as powerful as it is, found that you could create this structure with this contents, and it would get to this code path. And then it realized that disconnecting is interesting, and then it realized just maybe by chance that, oh, this specific ordering, use it after free just starts to pop up everywhere. And so this is the panic I got. And as you can see, this is a kernel built in February of 2022. So just a few months ago, this is a real app sandbox to kernel use after free. And it was found totally deterministically. I could run this test case 5,000 times. It would crash in the same way every time. It was straightforward to transcribe to by hand. And so that's actually this bug on the top from my initial list is, we started out with, thinking, at least for me, thinking this was impossible. By the middle of it, I'm colliding with people. And then by the end, I'm starting to find new things that are, until now, undiscovered. And it's possible that other people were aware of this bug, but at least as far as public source code and at least the latest iOS version at the time, it was there. So then my question was, what exactly did I even do? I just started from what made sense to me and just proceeded forward and forward. How is it that no one has done this? Is there anything interesting here? What am I observing? So I talked to a lot of people. I did a lot of research to try to understand how this fits into existing work. And it turns out that it's a real small tweak on deterministic record and replay, which is a type of research that people write papers on. It's like a very broad space. And Yeah, it turns out I just have a little twist on it that's related to security and fuzzing. So I think a couple of really good examples that are representative are the RR project, which is a reversible debugger from Mozilla. And a lot of companies have a reversible debugger. So if you think about what reversible debugging is, it means you run a test case and you capture all non-determinism to some file. Then when you rerun the test case, you need to be able to replay everything that you observed. And so, by being able to replay it, this is how you can reverse. So you're not really reversing, you're kind of going back to where you were earlier. And so if you think about it, if we run a program to try to capture a race condition, and then we output some file, well, who said that we have to specifically run and get that file to happen to be created for us? Why not just randomize this file? Why not just create this file ourselves? And that's really the thing that I've done here. So the other thing that's interesting is Microsoft Chess. This is another project that I think is maybe even a decade old by this point. And there they do actually the same thing. I really couldn't believe how similar it was. You have one thread, you replace the scheduler, so you control it. You turn off preemption, and you have a few sync points, which are yields next to mutexes. But the difference here is that they try to systematically enumerate all interleavings of a given thing. So in that first example, where I showed the binder thing, they might say, let's add a yield after this unlock, and then we'll test every possible interleaving of all the threads and all of these points and see if there's a bug. And so that actually would have worked, probably does work on a program like this. But the problem is when you want to scale this to an entire kernel, you have BSD, mock, you have millions of lines of code. It's really kind of intractable to guess where to run things. And I guess that's not the right way to say it. Like, I'm also guessing where to preempt. But rather than systematically testing every possible exponential number of interleavings in one specific place, I'm just saying, here's a way to explore everything, and the fuzzer can go ahead and try to just do it for me. And so, in summary, I guess the two contributions I think that are really novel here are that we now have this, we now let a fuzzer control interleavings, and we also, this part isn't really new, but we scope down annotations and, we scope down where we do the yields. So annotations of like yielding and blocking and stuff, so that it only happens in a few places where we think bugs are likely to happen. And again, my model is sort of like IDA Pro. It's if the researcher is competent, just allow them to express what they want to express. So as long as we can give a security researcher this tool and they have good hypotheses, good intuition about race condition bugs, they should be able to use it to explore on their behalf to do experiments. And so future work in this area thus far, I have not done anything to inform the fuzzer about these different threads. So it doesn't understand, like, maybe in that binder case, like, oh, it's kind of interesting that these two threads are near each other using the same data, and we should interleave around here. There's no, I honestly couldn't believe that this worked at all, but somehow, I think what's happening is coverage-guided fuzzing just works so well that random schedules are enough to find bugs. And importantly, if you're randomly building a test case and growing it using coverage-guided fuzzing, it's actually pretty likely you'll end up with two threads doing work related to each other. So the fuzzer might notice, like, oh, if I'm doing stuff in this thread, but in the other thread I mutate, and that affects this thread, maybe it deletes something that I was trying to use. That's sort of interesting. So the fuzzer's kind of building this thing, and along the way, it gets close to a state where a random schedule might just trigger a specific interleaving that's buggy. And then obviously improving performance, productionizing this. But essentially, I think I have the, I had the idea, I did the implementation, was able to replicate existing work and find new bugs. And so essentially ready to say that I think this project succeeded as a research project, and it's just a question of shipping it. So in, I guess, the way that these things normally go, it is not ready to be shipped. So there will be a first draft available on the Project Zero GitHub. The Sock Fuzzer project is already open source, and we'll be adding this multi-threaded fuzzing component to it shortly, probably in the next week or so, once we merge a few final improvements. And I think I'm out of time, so let's just leave it at that. But yeah, basically, coverage guided fuzzing is amazing. We need to work more on concurrency, and not just for security. We need much better concurrency tooling, and it's not that hard, I think. So this is kind of my takeaways. So yeah, thank you, everyone. I think we're out of time, so probably have to do questions outside, but appreciate you coming.